Welcome to the September 11th meeting of the Makery. Okay, so another quick summary for those of you who are new here or haven't been to our other meetings. So we have weekly meetings this semester every Friday from 6:30 to 7:30 p.m. via the BlueJeans link that you probably used to get here. If you haven't filled out this form already, it's tinyurl.com/gtmakerysurvey2021. So that'll let you put in your email so that we can add you to our email list, and then you can also fill in some ideas for workshops that you want to see us doing for you. On usual semesters, we also do these long-term projects, and right now our biggest one is a go-kart using decommissioned Lime scooters. So we got the motors from Lime, and we are putting them together to make a car. Fortunately, with COVID, we're not really able to do much work on that, but hopefully we can do more on that in the coming semesters or later this semester if things clear up. Okay, so this workshop, we're doing it a little bit differently. There's not going to be a whole lot of physical Arduino stuff. We want to do a purely Tinkercad workshop. We really want you guys to follow along. We're going to have a couple check-ins throughout the meeting where you guys can screenshot what you're doing so far. So you can go to, you can either just Google Tinkercad or you can go to this link and then you can create a free account, and from there you can build any circuits that you want, and you can also write the code for them and simulate. And yeah, in general, for our other Arduino tutorials, if you want to watch past recordings or in the future, you can also go to tinyurl.com/gtmakerykit, and that is an Amazon link to an Arduino kit that we picked. We think that one would be pretty comprehensive for all the workshops that we would work on.
That said, the kit is obviously not required. It's just if you want to follow along or if you want to get involved in Arduino on your own, then this kit would kind of give you everything you need to get started. So just if you want to get it, get it. If not, that's perfectly fine. You should be able to follow along pretty well just by watching the live stream or by checking Amazon or checking Tinkercad.
Okay. Now let's move on to the actual lesson. So let's see what an ultrasonic sensor is. So an ultrasonic sensor is used for measuring distance. So the way it works is it has a transmitter and a receiver. So you can see there's a little T right here and a little R right here. So the way it works is the transmitter will send a sound wave out, and then it will bounce off of an object and then come back into the receiver end. So then you can send a voltage on this trigger pin, and then it'll send the sound wave, and then you can read on the echo pin, or once the sound wave comes in, that pin will go high, and you can read that time delay, and that will allow you to measure your range. So this is just a very simple wiring of the ultrasonic sensor. So you have your high and your low connected to the Arduino, and then your trigger and your echo pins connected to any two digital pins on the Arduino. That's ultrasonic sensors. So does anyone have questions about how an ultrasonic sensor works before I move on? And also, was everyone able to set up Tinkercad? So it seems like there's not questions for now. Again, feel free to put questions as we're going, and then we'll get to those as we can. So now let's look at controlling motors. So one of the biggest things that you'll see with motor control is the use of transistors. So you can use transistors to limit the amount of power going through the circuit. So you can see right here, there is an N-type transistor, which you can see by this little N. So what a transistor is it has a source and a drain. So where the power comes from and where it goes to, and then it has a gate. So the way an N-type transistor works is when there's no voltage at the gate, then the circuit is open, which means, so it's a little bit confusing, but open means that current cannot flow. And then when the gate has power, then the gate is closed, and that means that the circuit is complete. So this allows to regulate the amount of current flowing from this power into the motor and then through the ground. Yes, this meeting is being recorded, so if you missed the first part, then we will send you the YouTube recording on either like Sunday or Monday. We'll try to get it out as soon as possible, and then you can watch the first half from there. So does anyone have any questions about transistors? I know transistors are a very confusing topic, and I didn't really go that in-depth on them. So does anyone have any questions before I kind of explain what this H-bridge means? Okay, I will just continue teaching then, and feel free to put in questions while I'm talking. So the way this H-bridge works is it's a set of transistors that are oriented in a way that allow us to either, depending on which voltages we send, we can turn the motor in any direction we want to. So we can see we have this VCC, which is like our logical high, or like our high power. And then we have this right here, these three little lines, that's an abbreviation for the ground. So power is going to go from this high and then through the circuit in some way, and then out through this ground. And then we have these four transistors here. So you have a P-type on the top of each side, and then an N-type right here. So P-types they let power through when there's nothing at the gate, and then when you send a voltage to the gate, it opens the P-type transistor, so then no current flows. So then, if we think about how this thing works, if we send a high voltage to both of the left side transistors and a low voltage to both of the right side transistors, so then let's look at what happens. So this P-type is getting a high voltage. That means the circuit is open and no current will flow through this branch. And then this one is an N-type, so when we send the voltage, it opens the circuit, so then current can flow in this branch. On the other hand, here we have a 0, so this P-type is open, and then this 0 closes, I worded that the wrong way, sorry. So the 0 here leaves the P-type closed, so current can flow, and the lack of power here leaves the N-type transistor open, so then current cannot flow. Again, sorry about the wording, it's quite confusing, and yeah, there's not much we can do about it. It's just the open close is almost completely backwards from what we would expect. So then, as we can see, the power would go through here, and then this P-type transistor is still closed circuit, so it can go through, but then this N-type is open. So then the power goes from here through the motor, going from the minus to the plus side of the motor, and then here, we remember that one is open circuit, but this one's closed, so it goes this way. So the power is going from the negative to positive of the motor, right? But then what is the difference between P-type and N-type transistors? So P-type and N-type are the two types of transistors. P-type is, so there's two different properties. So P-type is connected to power, so like P for power. So when the transistor is letting current through, it's going to be letting power through from source to drain. And then an N-type transistor is connected to ground usually. And the mnemonic is a little bad for this, but ground has an N in it, which means it goes with N-type. So when N-type transistors are closed circuit, they're letting current through, they are sending voltage, it is draining to the ground for an N-type transistor. So then P-type transistors, they are normally closed, so then current can pass through a P-type, but when you send a high to the gate of a P-type transistor, it cuts off the current flow, or it opens the circuit. And then N-types work in the opposite way. When there's no voltage at the gate of an N-type transistor, then the current cannot flow, but then when you send a high to the gate of the transistor, the current can flow through to the ground. So you can see right here we have both of the N-types are letting current through to the ground, and then the P-types are letting the high voltage come through. So P for power, and then N has the ground has that N in it. And so whenever I said no voltage, take that as 0 voltage. Sorry for the confusing terminology. Okay, so now let's look at the other case. So when the right side is both high, then this P-type is closed or open.
Did that make sense, or did you want more clarification?
Oh yeah, sorry about asking.
Awesome.
Very cool. Okay, so now we said when these two are high and these two are low, the current flows like this. Now let's see what happens when transistor 3 and 4 are high and 1 and 2 are low. So transistor 3 high opens this circuit, current doesn't flow. High over here closes the N-type so current can flow. And then on the other side, the 0 lets power through here, and the 0 lets no current through here. So then this time, our power will flow through this P-type transistor, and then from positive to negative, and then through this N-type and to ground. So we can see that by sending a 1 to both of these and a 0 to both of these, we can spin the motor in one direction. But then when we send the 1 here and the 0 here, the current flows in the other direction, and it makes the motor spin in the opposite direction. That way we have, it gives us an easy way to just have two power lines that we can write to a high and a low to both of those, and that'll just determine which direction the motor can spin. So does that make sense for why we can use this to spin the motor in both directions and why we would use this? And again, you don't have to ask your questions in chat. If you feel like unmuting and you're comfortable with that, you can unmute and ask your questions too. Okay, sounds good. I will move on. So now let's see what this little circuit component is. So this is an L293D, quad half H-bridge motor driver. That's a really long word for basically it's just 4 half H-bridges, which is essentially just 2 full H-bridges. And this allows us to control 2 motors independently with both forward and backwards control. So let's look at what the different pins on the H-bridge are. So we have our VCC, like we saw, and then another voltage in, right? So this VCC1 is used to determine what our logical high and low will be. So again, if you remember on the previous slide, when we're sending a high voltage here, that determines that this one should be closed and this one should be open, or this one should be open, this one should be closed. So it's basically that's going to be relative to this VCC1. And then this input 1, 2, 3, 4. So that's the inputs to each of the H bridges. So it's a little bit confusing. It's not transistor 1, transistor 2, 3, and 4 from the previous slide. It's actually, this one is going to both transistor 1 and 2, and then this one goes to both transistor 3 and 4. So input 1 and 2 correspond to both directions of one motor, and then input 3 and 4 are related to both directions of the other motor. So that's why it's called a quad half H bridge, because there's 2 of the full H bridges. So these are one input, these are one input, and then you have another whole entire this thing for the other motor. And then these are your ground pins, and then this VCC2 is where our actual motor power comes in. So this is the motor, this is the power that will actually drive our motors, because our logic level high might not be enough, or probably isn't enough to actually drive the motors, which is why we have this. And then these enable pins are almost, for most use cases, you'll just always have these set to high, and that's basically just enabling the inputs to control your motors. And then, so this output 1 and 2 corresponds to the high and low for your first motor, and then 3 and 4 are the high and low of your second motor. So does that make sense to everyone, how this component is essentially 2 of those H bridges in one little circuit? Okay, seems like there's no questions so far. Amazing. Okay, now we will start our Tinkercad. So everyone, hopefully you have Tinkercad pulled up. And again, it might be a little bit difficult if you don't have multiple screens to see the Tinkercad and this call at the same time. So I'll try to be descriptive when I'm talking so that you don't have to switch your windows as often. So if you're building this physically, this is some of the stuff that you would need, but we're going to be working in Tinkercad. So I will switch over to that now. Okay. So the first thing we want to do is we want to pull in a simple Arduino. And let's go ahead and we'll use, okay, whatever. I'll pull in this one. Tinkercad might be a bit slow. It is for me. So we have this. So we have the 5-volt and ground coming from our Arduino. But rather than having both of our power rails be the Arduino-based 5 volts, we can have our own battery, which will use as our the voltage we use to drive the actual motors. So let's pull in an actual battery. So I will just put this right here, connecting the two ground rails because the ground would be the same regardless. And then let's pull in a battery. Potato battery. So as you can see, Tinkercad has a potato battery, which you can totally just use to send insane amounts of voltage that aren't actually possible. Let's color code these wires just so it's clear. Oh my.
You can use a regular battery instead of a potato if you want, by the way.
Yes. And you'll need this to be relatively high. So it needs to be 5 to 12 because basically what we're going to do is we're going to use this battery to not only power the motors but also power the Arduino. And an Arduino can be powered by between 5 and 12 volts. So we'll just put this at a nice 10 volts and we'll make our internal, oh no, I deleted the battery. We'll make our internal resistance very low because we have magic potatoes.
Cool.
What is the difference between the lemon and potato battery? They're just two different batteries. This is not a chemical engineering class.
Potato and the lemon just follow different electrochemical properties, but they have a copper lead and a zinc lead in them. And basically the acid that is inside the fruit or the vegetable will provide you with the potential difference for your circuit.
Now we have our battery wired up, or actually we don't have it wired up. So to use this, in order to use this battery to power the Arduino as well, we have this VIN pin. So I'll zoom in just so that you can see it. So we have VIN. So what you can do with an Arduino is you can actually power it from this VIN pin as long as the voltage isn't too high, or else it'll just destroy your Arduino. So we'll drag ourselves a wire. I'll try to be neat with the wires, but it's a little bit hard unless I spend 10 hours making every single wire perfect. Okay, so now we have this power wire coming in, which is connected to the same ground rail as our battery, coming into this VIN. So what this allows us to do is you can have a battery powering your Arduino without having to plug anything into this power port on the bottom left. So it's a little bit different in Tinkercad because when you start the simulation, this little wire that comes from your computer gets plugged in right here. But in actuality, you wouldn't have to have this plugged in, and you could have this potato powering the Arduino without a battery here either, because the battery is being wired through VIN rather than from the power cable. That basically allows you to not need an adapter. Okay, now we have our power wired up. So now let's get our H-bridge installed. So let's look for the L293D, half-bridge motor driver. So bring this in, and we'll just stick it in right here. So for any of you who are following along, are you able to keep up? Am I going too fast or too slow? Or, yeah, how's everyone's progress so far? A little fast. Okay. Oh, okay. So I'll try to slow down a bit then. Sorry about that. So fast in what sense? Like I'm moving on too fast, or like my explanations are too short? Tinkercad is just slow. Yeah, I agree. Yeah, we all just have to deal with that. Okay. So we have our L293D in here. So now let's connect our enable pins. So we can do that first. So we have our enable 1 and 2, and then our enable 3 and 4. So those both need to have our logical high, which is the 5 volts from the Arduino. We don't want to put in this potato voltage, or else it'll destroy the H bridge. So we'll wire this power rail up to here, and then so we can color that red, and then we'll bring another one. Again, sorry for the wires looking disgusting, and that'll come to this rail, also red. Or okay, so what I'll do is I'll color the 5-volt ones orange, and the high power ones red, just so that you guys can easily differentiate between like what power level is going where. Okay, and now, so we have these enable pins, but then as you remember, we have this power 1, which needs to be the reference level for the logical high. So we'll pull this 5 volts, which we're using as our logic level, and then we'll wire it to this guy. So now our power 1, which is our logic level, is wired to 5 volts. And then we need our driving voltage, which is this red rail at the top, to come to our power 2. So we'll bring this guy out. Someone let me know if these wires are unbearably messy, and I will try to clean them up a bit. And also, so at the end of the PowerPoint, we will have a link to to the actual Tinkercad file I used, and that one has it much cleaner and nicer to look at. You can use that. It's also kind of hard to see what pins are connecting. Okay, so I can zoom in a bit. Is this a little bit better for you guys? So now that we have our logic level set up, let's make sure to connect a ground as well to the H bridge, or else you'll become very sad like I was when I was trying to plan this workshop. So we can see this is our ground. So we have 4 grounds. We can just connect any one of them. So I'll just connect this one, and then I'll just attach it to this ground rail. And the nice thing is that both of our ground rails are the same because they're connected. So like the ground relative to the battery is the same as the ground relative to power. So it doesn't matter which ground I wire it to. And then so now we can start putting in our motors. So I will pull in 2 motors. Let's search right here for motor. That didn't type. Motor. So is everyone able to keep up with where I am so far? You have your highs and lows wired up for your control? Oh no, I spun it too far. There we go. Now we will imagine this one is our left motor and this one is our right motor. So our car is facing towards the right side of the screen. I can, but I don't want to. Okay, now we need to wire up all of our inputs. So we've taken care of everything. Now we just need to do the input and output of each of our 2 motors. So let's do motor 1 first. Okay. So we'll want to use PWM pins for all of our inputs and from the Arduino to the H bridge, and that way we can not only have like forward and reverse, but we can have different speeds of forward and reverse. So we'll have pins 5 and 6 on the Arduino control the right side motor, which is going to be on this side, and then we'll have pin 10 and 11 come around to this side. Let's look. So we'll have pin 5 coming up here, and then it'll come into this input 2, and we'll have pin 6 come here to input 1. And we'll have, I'll make these input 2, I'll make this one, I will make this input 1 purple, just so that we can differentiate between like the forward and reverse of the motor. Can everyone just like ping in chat of if they're following along? One moment for the wires. How do I unrotate a component? So you can just continue clicking the rotate button and just like do a full 360. That's what I had to do as well. I have to switch screens, so I've given up, but it makes sense. Okay, yeah, sorry about you having to switch screens a bunch. Maybe we can try to figure out something for next meeting that won't necessitate you doing that, but yeah, hopefully you can still learn along the way. Yes, one moment for the wires. Yeah, I'll continue to just slowly wire. So we have 10 going to the input 4, and then we'll have 11. I'll switch it to purple once I place it, going to input 3. Purple. Okay, so now we have all of our inputs wired up. So now let's take our outputs to control the motors. So we'll grab, so we can see this one is output and this one is output. So we'll grab a wire from here that goes to the power of the motor. So the red or positive terminal of the motor will come from input 2. And then the input 1 will control the negative of this motor. Again, sorry about these wires being completely disgusting. And then same thing for this one. We'll have input 4 connected to the positive terminal of our motor. So I'll just come around the motor so that we have less energy. And input 3 controlling the connected to the negative terminal of our motor. Okay. So has everyone made has everyone set up their H-bridge with their motors in Tinkercad? Adding the motor. So we have our motors wired up. So now let's also bring a potentiometer in, because we talked about using a potentiometer to sense distance. So maybe what we could do is we have this little car with these 2 motors, and then you can imagine if we wanted to have 4 motors, you could use a similar setup to also have another 2 motors connected. So what we could use is an ultrasonic sensor. We could essentially put that at the front of the vehicle, and then although this is Tinkercad, so obviously our vehicle can't really crash into anything, but if we're making an actual motor, an actual car, we want it to not just crash into everything. We could have an ultrasonic sensor that basically when things are close to the ultrasonic sensor, or that time delay between sending and receiving the sound wave is very short, we can have it slow down the car or maybe even go in reverse so that it doesn't just like go straight into a wall. And obviously you could extrapolate this into having an ultrasonic sensor on the back and the left and the right so that it always senses when there's walls nearby, but we'll just do one in the front for now. Right here, we will just search ultrasonic, and we'll pull in this guy. So right here, and then let's rotate it just so that it's kind of facing forwards. And then we will connect this power pin. So we'll zoom in on the potentiometer. We have a similar thing. So VCC is going to be our power coming in, and then this trigger pin, when we write high to the trigger pin, it's going to send out the sound wave, and then we will read on the echo pin, and we'll be able to measure the delay until the echo pin goes high, which is when this echo pin receives the sound wave back, and then this ground pin is just like, yeah, it's connected to ground so that it has the high and the low. Okay, so we will put this guy to here, and then we'll connect this rail to here, and we'll make both of these orange because these are representing our logical 5-volt high. And then we'll have this ground pin connected to this one, and this guy will put it to ground, and we'll make both of these black. So is everyone still able to follow along with what I've done so far? How do you rotate things again? So I think the camera might be over this part of your screen, but in the top left, right under the Tinkercad logo, there's a little there's two little triangles with a curved arrow. So if you click that while you're selecting a component, it will rotate it. Yeah, you can see that it's this button right here. So I can, I'll just pull in another motor to demonstrate the rotation. So I put this motor right here, and then while I'm selected, I can just click this, and it'll just rotate every time I click it. And there's no rotate backwards, so if you rotate it past where you want, you just have to click and go in like a full 360. Back. Now let's wire up the trigger and the echo pin of our ultrasonic sensor. Sorry. So we get this trigger pin. We'll come here, and then these don't have to be PWM. So I'll just go to digital pin 4, and I will make this turquoise, and then I will wire the echo pin to pin 2. Pink. Okay, so does everyone have a circuit that looks something like this? Hopefully yours looks a little bit better. So we'll move on now. So now we have our circuit fully built up, but we don't have any code. You can see when we start the simulation, nothing happens. These motors are both showing 0 RPM. I'm not sure if it's very clear. I'll just zoom in all the way. So on the motors, right here, you can see the speed at which they're rotating. So since we don't really have any code written to do anything, they're just at 0 RPM. Zoom out, and we can start writing code. Okay. So it'll start with block code, but hopefully you guys agree that you can't really do much with block code. Quite limiting for people that actually want to write a lot of code. Okay, so we have this generic setup and loop that Tinkercad gives us, but we don't want any of this, so we will just delete it. Okay. Now we will wire up our, so we'll do our pound defines like we did last week. So we will do hashtag define. So this is something that the C language uses, and Arduino is coded using C. So hashtag define or pound define. Oh, sorry. For clarity, it's C++ for Arduino, not C. And so what pound define does is you can type in this right here, and now wherever I have pin ultrasonic trigger, it will get replaced with the number 4. And then I can do the same thing for my echo pin. So pound define echo, this one will be 2. So as you remember in our wiring, the trigger pin, which is this blue one, is coming to 4, and the echo pin was at pin 2. So has everyone gotten to the stage where they're coding for the people who are following along? Yes, very cool. Okay. So we have our pound defines for the sensors. So now let's go ahead and pound define our motor control. So you can call these whatever you want. I like to have all of my defines related to pins start with pin underscore. That way I just know that it's referring to a pin, because if you come back to the code later on and you just see like digital write ultrasonic trigger, it might be a little bit confusing. So just having that pin underscore is something that I like to do personally. Okay. So now we'll create a define for our left motor that is for the forward. So left motor forward will be pin 10. You can see right here, digital pin 10, or the PWM pin 10 is coming around here into input 4 of the H bridge, and then it's coming out to the positive side of the motor, which is why we know that when that one is on, it's going to be going forward because it's coming to the positive, whereas input 3 is wired to the ground terminal. So when we have voltage going in that direction, it's going through ground first, so that would be reverse. So we will do reverse is going to be 11, right? And then we'll have the same thing for our right motors, but it would be 5, 6. So we'll change this L to R, and then we'll change 10 and 11 to 5 and 6, because right here we have our PWM pin 5 and 6 wired to these two inputs of the motor, again coming right here to the ground, to the terminal 2 and then 1. Now we have this set up. So now let's create ourselves some helper functions for both reading from the ultrasonic sensor and then writing to the drive. So let's write a function that will basically, we call the function and then it returns the distance that the ultrasonic sensor is reading. So we'll have it return a long, and then we can call it read ultrasonic. Here. Okay. So we start by writing to the trigger pin, right? So we digital write to the pin underscore. So I'll just copy paste this. So, and then what we can do is delay. So right here, these time differences can be extremely short. So what we're going to do is we're going to delay microseconds. So you might remember from before we used the delay function, but this takes in milliseconds. which are often too large for the small delays that you'll get from this ultrasonic sensor. So we will delay for 2 microseconds. And now what that's done is that we've confirmed that the trigger pin is low, and now we'll send our pulse. So we'll write it to high and then wait a couple microseconds and write it back to low. And that'll be like our quick little pulse. So write, and then we put a high, and then we want to we'll do a 10 microsecond pulse. So that 10 microseconds, that's just the standard that I found online that people use. I'm not 100% knowledgeable on all the different physics and timings of how an ultrasonic sensor works, but delay microseconds 10 for your pulse width is a pretty good measure. And then we have a function called pulse in. So what that does is that tells you the time it's been so it returns the time until something returns, until the pin reads high. Sorry, I cannot speak right now. Okay. We have our echo pin, and then right here, and then high. So this it'll return the microseconds for this to eventually read high. That's our time, and then we will just return inches. So to convert that, we will do, what is the function? Equals. Okay, so unfortunately, I have the number for centimeters, so I will just divide that by 2.54. So 0.1723. So this is going to convert your microseconds to centimeters, and then we will just divide by 2.54, and then we'll multiply this by our time, and then we will return inches. And we can have this be a long. Does everyone understand how this ultrasonic sensing function is written? Oh. Okay. So we want to multiply first because coding is hard. So basically what the issue is if we do this 0 divided by 2.54 first, it's going, because there's integer types, it would round down to 0 before we multiply by the time value that we had. So we want to multiply it first so that this is a large number, which then gets divided by 2.54. So you don't just always truncate to 0. So just to clarify, pulse in returns the delay from when the first signal is sent to when the echo is received. Correct. So it's returning the time from when the function is called to when the first parameter pin reads the value passed in as the second parameter. So if something is high and then eventually becomes low, you could do pulse in and then the pin comma low. But yeah, so it's basically, since we sent this pulse from the trigger and then we're reading from the echo, it's just going to read the time from when we send the trigger pulse to when the echo receives that sound wave, when it reflects off of some object. And then, so that is our helper function for the ultrasonic sensor. And so now we will create ourselves a helper function for writing to the drive of the thing, or to the motors. So we'll have 2 parameters, the left power and the right power. And so if we remember, the PWM is from 0 to 255, but then we actually have 2 different pins that we can send it. We can either send 0 to 255 on the forward pins, or we can send 0 to 255 on the reverse pins. So we have 512 different like speeds, going from negative 255 all the way to positive 255. So the one issue is that we can't write the negative values to the reverse pin. So we need to check if left is less than 0, then we'll send the positive version of left onto the reverse pin, and then we'll write 0 onto the right pin. So we want to do analog write to the pin left motor reverse. No, what just happened to my code? This pin, and then we want to do negative left, because left is a negative number, but we can only write positive values. And then we'll just do this, and the forward pin will be given a 0. Then else, which means our left is positive, we'll do the same thing. But the reverse this time will be 0, and our forward will be our left power. So does this little block make sense of how we can take in the negative 255 to positive 255, and then convert that into two different values that go to both the reverse and forward pins? And yeah, please ask questions if you have any. I know I'm going over quite a few different things at once. So now that we have our logic for the left, we will just do the same for the right. So if right is less than 0, we will do the following for the right motor. I saw there was a chat. I will look at that in a sec. What's the difference between analog and digital write? Okay, so digital write is going to be digital values. So digital is just high or low, 1 or 0. So that's why the ultrasonic is using digital pins, because it's just like you send it a high and it'll send the trigger, or it'll send the sound wave, and then you send it the low to cut off that sound wave, and then you read for when the receiver is receiving the sound wave, so then it would be high. Then analog, what that does, it allows you to send from low to high, but everything in between as well. So you have two types of analog. You have this like actual analog, which is at the bottom right here, these analog pins, and then you have PWM. So PWM, it essentially uses, so PWM stands for pulse width modulation. So that uses digital output or input to replicate the behavior of analog. So digital write of 128. So the analog for digital, like the PWM range for digital pins is 0 to 255. So if we analog write 128 onto a digital pin, what it's interpreted as is on for half the time, off for the other half of the time. So it's like 50-50. It's right in the middle. But then if we did like 255 over 3, that's like 80 or 90 or so, then it would be on for a third of the time, off for 2/3 of the time. And that essentially allows us to emulate analog signals with digital by using the pulse width modulation. So yeah, it's kind of in the name, pulse width modulation. So the width of like how long it's on versus off. Okay, so now we have our two helper functions, one that reads the ultrasonic and one that writes to the drive. So now let's get into our actual code to run the car. So in our setup, we will do serial.begin. So this is something you'll want to do almost every time you write a project for Arduino. So serial.begin 9600, that will set up the serial communication between the Arduino and your computer. So what serial communication is you're sending bits over the USB wire that's connected from your Arduino to your computer. So that would be this little wire right here, but obviously there's no computer since this is our fake computer. And basically what that allows you to do is you can print things from the Arduino onto the serial line, and then your computer, you can pull up a serial monitor where you monitor the signals coming in from that line, and you can basically have a console for your Arduino that you can use for debugging purposes. And this 9600 is the baud rate of the serial connection. Oh my goodness, I cannot speak. The baud rate of the serial connection. So that's the rate of binary data coming into through your signal line. Okay, so we have our serial monitor set up. So now let's set the pin mode. So every pin on the Arduino, it's nice if you set the pin mode of it, because that allows you, it basically just sets like this pin is always going to be used for input, or this pin is always going to be used for output. And so technically you can get away with not writing these pin modes, but it makes it run a little bit slower when you're using them as output or input, because it's not explicitly defined as only input or only output. So explicitly writing your pin modes helps your code for efficiency, and it also just helps with clarity of your code, because everyone can see what each of the pins is going to do. So does everyone understand what I was doing with the what the serial.begin was? Seems like there's no questions. So right now, so it's almost 7:30. I know I'm going a little bit slowly, and we should be able to finish by about 7:40, 7:45. But I can't see the line below serial. Oh, is it like too small? Yes. I don't know. Okay, that works. Okay. Is this more legible now? Yeah. Okay. So we set our trigger pin to be output, and then we want to set the echo pin to input. And then, so that's for the ultrasonic, and then we will set all of our motor pins to be output. So pin mode, pin left, motor forward to output. Motor reverse, and we'll do the same for the right pins. Okay, so does everyone have their setup function written? So now we are almost done coding. We're just going to write our last little bit of code in the loop. Okay, so it seems like there's not questions. Feel free to still drop your questions in the chat. And yeah, once again, sorry that it's already 7:30. If you need to go, feel free to leave. We'll have this recording up, so that'll be available for you to watch if you can't watch the rest of the meeting right now. Yeah, we should be able to finish relatively soon, so if you can stay on, feel free to just finish through with us. So we will now, in our loop function, we'll call that inches function, or we'll call this helper function that we made for the ultrasonic. So it's called read ultrasonic. Okay, and now we have our inches. So now let's go ahead and print this value to our serial monitor. So we can do print, and then here we'll give ourselves some units. Okay, so now let's go ahead and just run this code, and we'll see how the ultrasonic sensor works and if it's doing what we want it to do. So we have pull up the serial monitor and then start simulation. So you can see to work with your potentiometer. Well, it's not a potentiometer. Ultrasonic sensor. So when you click on it, it'll pull up this little field of view of the potentiometer. So obviously a physical potentiometer doesn't have like magic boundaries like this. It's a lot more like variable. There's a lot more noise involved in real world sensors, but you can see so we can move around this little object that it's sensing. You see it went from 44 to 79 in here. And you can see like right here we have this little 80. So yeah, you can see that it's a little bit off, and that's partially due to the rounding errors with the multiplying and dividing that we're doing, but it's still almost always like pretty close to what we want. And so then we can bring it down really low, and so it's 18, and right here we're printing 17. Okay. So is everyone able to call that ultrasonic sensor function and read those values and play around with the little dot in the field of view of the potential? Why do I keep saying potentiometer of the ultrasonic sensor? Oh, it seems to have some bugs. Okay. Is it printing anything right now? Or is it like not compiling, or I'll figure them out. Probably just some time. Okay, sounds good. So now we have our inches reading. So now let's figure out what power we want to send to our car. So this is a very dumb car. It's just going to always be going forward. It's just always full throttle forward, and then if it realizes that it needs to slow down, it will do so. So we can do if inches is less than some threshold value. So let's see, when we click on this potentiometer, the max value was about 130. So we can do if it's less than 130, so we see something in our way, we'll have some logic to slow down. So what we can do is I figured out this like little short equation for like decreasing the power based on how close an object is to the potentiometer. Obviously, you can figure out if you were actually building this, you would figure out your own like parameters for like when it's this close, it needs to go this fast. But I'll just quickly write in what I figured out would work well for this demonstration. Times 4. Okay, so basically what this function is doing is the 130 minus inches, so it's like the remaining distance from like the sensor to like the boundary, and then we multiply that by 4. So if inches was like 10 or like 30 or something, so something very low, this would be 100, and then that would get multiplied by 4, so 400, and then we subtract that from our power. So we do 255 minus 400, so that would be like negative 145. And then we can also add in like a failsafe that checks if the inches is less than, like, let's say 10, then we want to just go full reverse power, so negative 255. That basically will just like override our function. It's just like if it's too close, you just need to yeet out. Okay, so now let's print our power function, our power value. So we'll print pow, and then we'll give ourselves some. We don't have magical units. So what we can do is we can make this inches, and then we can say like this, like speed equals, and then this one will go to the next line. So the point of that is basically so we can have each line be related to one run of the loop call. And so it's personal preference how you print to your serial monitor, but I just find it nice when each line is associated with one run of the loop. So we've made our power, and then we've set the drive. So we want the left and right to both have the same power. You can imagine how if we had like sensors on the left and the right, we could set different powers. And I have a typo right here, so set drive. And then, so once you've set the drive to go at a certain speed, we want to have a delay within our loop. That's just to make sure our loop isn't just like, it's basically the delay helps to reduce the frequency of the loop, because when it's running super fast, it can,
it doesn't oscillate. right? You sit there like right at the boundary, and you just keep jerking back and forth because you're updating too fast.
Okay, now we have our code. Let's start the simulation and see what the car does. So we'll move our code out of the way. We'll bring the car in view. Okay, so you guys can probably see that there's some number right here. So it seems we have a bug already, because right now it is going negative 4,000, or actually no, let's see what the potentiometer is at. So yeah, that makes sense. The potentiometer sees something very close, so it's going negative 4,000 RPM. These are some seriously strong motors. If you have motors this small that go 4,000 RPM, you're, yeah. And then you can see when this is out of the range, the motor should start moving in the opposite direction. So you can see the value starts changing from negative to positive. I'm trying to keep everything in view, but it's still kind of small. Is everyone seeing that this is now positive, like 4,600? Yes. Okay. So let's try to move this here just so that I can get zoomed in. Oh my, that is down. Okay. Now, if I start the simulation, I can try to zoom in on just this little section of thing. Okay, so this motor, you can't see the speed value, but it's going to be the same as this bottom one, so I'll just zoom in a bit more. So let's, so can everyone see the potentiometer and then the speed of that bottom motor? Okay, I'll use this motor so that it's not upside down. So when I drop this like around the middle, we can see that it slows down to around like 2,700. And you can see that the value isn't super consistent, and that's just because the motors aren't super consistent. So what you could do is you could have sensors on the motor or like some wheel that's connected through gears so it's not like spinning that fast. So then you could check like the rotation speed and use that as a measure of like, I want to go this fast, but the motor's actually going a little bit faster, so decrease the power of it. So you could use like some sort of like sensor control based on the actual motor output for relative to what we actually want it to be. And then when we're close by, the motor should start slowing down, and now it's going negative. And then when we put it like all the way close by, it's going negative 4,600 RPM. So that is our car complete with a little ultrasonic sensor in the front. So hopefully, do you guys think that this was a little bit better in fully Tinkercad so you guys could follow along with us? How did you guys feel? Would you rather us build the physical models and you just watch? Or did you kind of enjoy being able to follow along and build this with us on Tinkercad? Awesome. Very cool. Okay, so we'll try to make most of our Arduino workshops like more interactive via Tinkercad. So what we'll try to do from now on is, less blurry too. Okay, so lots of pros related to using Tinkercad. So we'll try to have most of these workshops in Tinkercad. So obviously there's a couple things that Tinkercad just isn't perfect for simulating, but if we realize that's the case, it would be in person. But otherwise, we'll use Tinkercad, and we'll try to have a physical model there for you at the end, so we can show you like a final product. Unfortunately, we don't have that for this one. We can maybe show you at the beginning of next week before we get started with 3D modeling. We can show you a small little car. Okay. So let's just. So yeah, if you're building this, if you're reviewing these slides later, and you got like the Arduino kit, or you want to retry it without guidance on Tinkercad, you can use these steps. And right here, this little link will take you to a much prettier version. So let's let this load for a sec. So you can see this looks way neater. All the wires are straight. They're not angled all over the place. So maybe you can use this for a more clear representation for you to go off of if you want to try this again. Okay, and with that, next Friday we will be doing 3D modeling with, so 3D modeling is apparently a little bit more complicated than computer-aided design, so we're going to be doing computer-aided design. And if you want to prep for the workshop, you can do tinyurl.com/downloadfusion. JJ, can you send that link in chat? But if you don't want to download it right now, we'll also give you time at the beginning of next meeting to get this installed. Okay. Thank you everyone for coming. Again, we meet every week on Fridays, so it's this exact time you can come back. Same link. Again, this is our survey, and then you can join our Discord, follow us on Instagram, or join the Facebook group. And you can also join the Slack, which will mirror all the communications we send on Discord. And we can send all those links in the chat as well. What are we modeling next week? Next week, we will be modeling a copper finger. So that's just the first thing that comes to mind when I think of this. You can Google image copper finger. There's probably a more generic name for it, but yeah, it's like the little thingies that you use to open doors without actually touching the door handles. So we're going to teach you a couple different functions in the Fusion 360 for the different the 2D and 3D tools within Fusion 360. So yeah, if anyone has any questions, drop those in the chat or unmute. And thank you everyone for coming. Goodbye if you're heading out.